Okay, now with that, I want to come to the main attraction of the event, or the main attraction of this particular movement so far, and that is the keynote talk by Urs Hoelzle from Google. In this particular audience, he does not really need an introduction. He has been a legend when it comes to network infrastructure and the web infrastructure and so on. So I thought I would only try to make 2 points about Urs. First is, if you look at this particular growth chart for Google, again, this is one of many ways to look at the growth of Google. The details do not matter, obviously, but you can see the pattern, you can see the trend. Urs started here. Even before Google had any revenues, he was the first VP of engineering at Google, before Google had any revenues. Today, he is the senior VP of technical infrastructure as well as a Google fellow. Now you can see the huge impact he has had in success of Google, all the way from pre-revenue to where it is today. And through Google having an impact on the society at a large as well. I'm sure we all know that this is very, very impressive. Not only that, if you take a closer look, through all of this, he has not aged at all. I look at his picture from before and now, and I see that he has not aged at all. Now, I want to make one more observation in the context of OpenFlow and SDN, and that is, he has been a champion, supporter, as well as a practitioner of OpenFlow and SDN. Though he is not considered an inventor of OpenFlow or SDN, it turns out he and his team have been practicing what can be thought of SDN for some years, right? And since then, he also quickly understood the value of OpenFlow and SDN for the larger networking and cloud infrastructure community, and has worked very hard to bring OpenFlow and SDN where it is today. And we thank him for that. And with that, here is Urs as our keynote speaker.
Thank you, Guru. Wow, after such an introduction, I hope I'm not going to disappoint you. And I just decided to change the topic of my talk. So instead of OpenFlow, I'm going to talk about the magic pills that keep me young, and you're going to have a chance to buy them afterwards. No, I really am here to talk about OpenFlow, and more specifically, what we've been doing in Google. So I'll show you that sort of how we run our backbone, and then what we learned in what makes it hard to run such a backbone, and how OpenFlow is helping making that easier. And so I hope to convince you that in the WAN case, which few people today talk about for OpenFlow, everyone talks about the data center. In the WAN case, there's actually a very, very compelling use case for OpenFlow. So why do we worry about our backbone? Because we have a lot of traffic. Here's one study from 2010 that looked at our external-facing internet traffic. We have, of course, lots of applications that generate that traffic. And then on top of that, what you don't see is we also have a lot of traffic on our internal backbone between the data centers. You know, data replication, the index push from our search engine, you know, et cetera, et cetera. Now, if you look at a WAN, a large WAN like that, what you would like to see is that, like when you run a larger data center, it's cheaper per unit to run a large thing than a small thing. And unfortunately, in networking, that's not really true. Or it certainly isn't as true as it could be, and it certainly isn't as true as it is in a data center, right? We've shown, for example, that when you run a large application like Gmail, you can, compared to a small organization running their own email server, you can save literally something like a factor of nearly 100 in terms of compute and energy when you run it at scale, right? In a large network, there's nothing like this. And there are a number of factors that make it hard to save money, even though you have a lot of devices and a lot of networking. Some of these factors are really, or many of these factors have to do with manageability, right? Many of these routers need to be still set up and configured by hand, and so you have more like a linear growth of your cost with the number of devices. And then the devices themselves tend to get more expensive per unit as you scale up. in part because they run routing algorithms on it that kind of scale with something like the square of the network or whatever. So you need to buy more expensive CPUs, more expensive controllers, and so on and so on. So this is something that makes us unhappy, because obviously we'd like to have better economics, because many of our products are offered for free. So it's not like we have a lot of margin in running them. We believe a solution to that is basically to do the same thing as you do in a data center. In a data center, when you have 10,000 machines, you don't actually manage those 10,000 machines individually. You don't actually log in to that machine and configure it. You have some kind of system that manages them as a pool, right? And then you dispatch your applications on it, etc. And it's mostly automated, so that when you manage these machines, you can't really tell the difference between managing 5,000 and 10,000, right? It's basically the same thing. And so we'd like to do the same thing in the network, where the individual box, the network box, isn't actually what you manage. It's really the overall assembly of all the boxes, how they're configured and how they work together to accomplish sort of the overall goal of the network, how they manage the traffic flows on that network. And really, you want to focus your management effort on those traffic flows, right? On the applications, on your Gmails and your YouTubes and where they go, and not on each individual box. And you also don't want to think about what happens for each individual box when it fails, right? Or when a link fails, right? That should all be sort of reconfigured and maintain the environments that you put in the network. And that's not very easy with today's networking boxes, right? They're all kind of intended for manual configuration. Different vendors have different ideas of how you can monitor them, how you automate them. It's all relatively low. So I'll show you some more examples of why this is not just expensive to run, but also relatively inefficient in the network. Here's a relatively simple network where I want to see what happens when a link fails. So look at this from kind of left to right. The round circles with R's are routers. Then you have links with certain capacity. And let's assume we have these 3 flows on that network today at different sizes. And now let's assume that one of these links here breaks, right? You have a fiber cut, whatever. So in today's network, what happens is that the adjacent router, R5, tells all the downstream routers or upstream routers that, hey, my link disappeared. And now each of these other routers in the system will autonomously try to kind of reconfigure itself for the new world, right? And they're each responsible for one of the flows that you just saw that, all of which are broken, and they're going to try and repair them. And so when you retry, one of them is going to be the first one, and he's going to book, the bottommost link, right? And the other 2 may have also tried to use that link. They will now fail because the reservation for this path will fail, and so they will retry, right? So someone else wins the next round, someone else wins the next round. And so there's 2 problems with this approach. First of all, it takes a while for the network after its link failure to kind of settle again, right? Because that, all the boxes kind of need to redefine their world and figure out what's happening. Second, this isn't deterministic. So after the same link failure, if it happens twice, what happens, the state after the failure may be different, just depending on what the timing happened. And in fact, what's even worse, it might be that sometimes the network succeeds in finding a new state that works for all flows, and sometimes it doesn't. Because if the first guy happens to partially use up one of the paths and block it for a larger flow, then that next larger flow might not find a home, right? And so you might actually have a broken flow in the network. And you can't tell sort of ahead of time. There are of course, ways to get around it. You can try to prioritize things, etc. But it's very hard because you need to go think about each individual situation. Now, hypothetically, if you had a more centralized solution where you have same network and now this square box, which is a central traffic engineering box, then you could kind of rejigger this a little bit and say, hey, if the same failure happens again, then R5, which is the closest box, just tells that traffic engine, hey, this link went down, and now this central engine decides what to do. They see, that engine sees the whole network. It knows about all the flows, so it can in one shot compute what the next, what the future state should be, tell all the routers what to do, and then we're done. So a much better, faster way of doing it. It's actually simpler because algorithmically, if you see everything, it's much easier to figure out what the next step should be. And it's also deterministic, right? Every time this happens, the same reaction will happen unless your inputs changed. So to recap, right, if you have a more centralized management of your network, and really this is all about traffic engineering, where you want to guarantee certain quality of service for the flows that are in your network, you can get a better network utilization because you can compute the best placement of all the flows worldwide given your network and given the demand. And when something fails, you know that you can have the next best optimal solution for the flows in this diminished network. So you never leave capacity over because left over, and you don't have to provision extra for these kind of unpredictable side effects. It's fast, so you can, even with a large network, you can compute a new solution very quickly. You can pre-compute solutions for every single element failure, etc. Right? It's easy to make this fast, and when I mean fast, I really mean 1 second plus whatever propagation delay you have worldwide, but the order of 1 second. And then more importantly, once you have that, you can reason about the network in a much better way, and you can actually have the inputs be more understandable to your application programmers. In a conventional network, if you look at the network configuration, you cannot tell anymore what Gmail is really and how you're treating it, or what YouTube is and how you're treating its traffic. That's all lost in very low-level mechanisms. And if you have a more higher-level sort of central point to do, you can actually use that as an input and say, for example, Gmail traffic is more important than YouTube traffic. So whenever you have to compromise between the two, pick Gmail. And then more importantly, or actually, often forgotten, but really very importantly, when you have the centralized view, it's easier for you to do software testing. And I'll show you a little bit why. So clearly, you're trying to manage a large network. You try to be not having bugs in that network. And in a conventional setup, that's actually pretty hard because each box runs a very specialized, highly complicated stack, and you need to have all the boxes kind of interact, and there's not even the signals that you feed each of these boxes is different, et cetera, et cetera. In this kind of way, you have one traffic engineering server. That traffic engineering server, as a regular part of its operation, needs to get all events in the network, all the control events. And so it's easy to capture them at that point and, for example, replay them later for the testing of your next release. Or just generally speaking, it's easier to build in testability into this kind of framework because you run it in a standard environment, standard software environment, and you can play with it. So that's what we did, and that really helped a lot. So we're trying to test the modules that we have in isolation, of course first, right? You do the unit tests. But then we also have a test bed that lets you simulate essentially the entire backbone on your workstation or on some server in the cloud. And so you can play through a lot of scenarios. What happens if two links fail at the same time? What happens if one element misbehaves and the link flaps, or et cetera, et cetera. And all of that sort of moves the project more into the realm of how you would run a large software project that is about distributed software. So in a simulated WAN, we have real binaries, both of the traffic server binary and the OpenFlow agent that's running on the switch. The hardware, of course, is virtualized. The network, of course, is virtualized. You can't do performance testing in this scenario. That's not what it's for. So you can't say, can I really carry line rate traffic or whatever, right? But you can simulate an arbitrary topology. You can simulate arbitrary failures. You can have simulation at scale. You can feed in captured old event streams, etc. And it's high fidelity enough where we could actually develop our monitoring software before we had a network by basically pointing the monitoring software at the simulated network, and it generates, because it's running the exact binaries that run in production, it's generating the same signals that you would normally see. So you can actually test your monitoring software as well in the simulation environment and see whether, for example, your alerting for a certain condition actually is in fact triggered by that condition, right? You just run that condition in your simulated network, and then you see whether your monitoring software gives you an alert. Here's a little snapshot of our development. You can really see this kind of overlays 2 releases, actually 3. So you can see kind of one valley in towards the left. That's where we sort of started to seriously roll out the first version of the network, and its bug count of that release kind of goes to 0. But then the development started on the next release that had traffic engineering. You'll hear a little bit more afterwards. And actually, most recently, the future release is kind of pushing the bug count up again. So just to recap, why are we excited about a software-defined LAN, right, rather than a software-defined data center LAN or enterprise LAN? Well, it's because all of these very nice properties that it gives you. It makes the management easier, and you can pick the right tools for the right job, so to speak. So I'll give you the one punchline. Literally, the server that you run on your traffic engineering on, compared to a server that typically is built into even a high-end router, is literally 25, 50 times faster. Right? So it's very easy with a modern, 32-core workstation to do things that are very, very hard to do on your embedded processor that sits, in a networking box. So really, a lot of things become easier, and you can use all the tools that you normally use for regular software development. And so that makes the software both faster to develop and higher quality. So now let me switch to, so after showing you all sort of these advantages in theory, let me tell you a little bit more how we try to put that into practice. So first, a word on our WAN. It's really kind of a misnomer. We have 2 backbones at Google. One is for traffic that goes to the internet, so to the user, and one that is for traffic between our data centers. These 2 backbones have very different properties in terms of what we want from them, right? Like user-facing is very latency sensitive. It better be super reliable. It has to interface with the rest of the world, so it has to be, very standards compliant, et cetera, et cetera. So we have a relatively conventionally built backbone for that. Lots of vendor gear. Sort of, it looks like an ISP, right? It is basically the ISP for Google, and so you'd recognize sort of all the elements in there. The second backbone is the internal backbone. We sometimes call it a G-scale backbone, and that's that carries bits between data centers, and more precisely carries bits between data centers that have a little bit lesser SLA. So that could be storage replication, search index replication, all kinds of other copy jobs for development, and so on. It carries a lot of traffic, but that traffic does not have a 5 nines type kind of requirement, and this is the backbone where we experimented with OpenFlows, because it's tolerant of some failure, but at the same time, since it's big, it's still very expensive to run and complicated to run since there's many devices in it. So we wanted to see if we can get the advantages on that WAN. Here's kind of how it looks like. Basically, the boxes are the data centers. They're public, so nothing new here. And this network connects our data centers, and this is basically the network as it is built out today. This is what it runs on. We started this project in 2010. We could not buy any OpenFlow hardware. Actually, we started it in 2009, and depending on how you count. So what we built is basically a 10 gig switch, 128 ports, and built from standard chipsets that you can buy, so there's no custom ASIC, no nothing. So pretty simple bug, a simple box. You see an early prototype here, and it runs almost no software on it. So other than the software you need to kind of bring up the box and initialize your cards and etc. Like the actual hardware control, it runs an OpenFlow agent and nothing else. So everything else is done in a controller. So there's no routing protocols, not even a CLI on the box. So even the CLI runs on the server. Because we wanted to experiment with how far we could get with moving software off of the box, and we didn't have to go back. And obviously it doesn't support every routing protocol. It just supports the routing protocols through the controller that we need. In our case, BGP and ISIS. Here's how you can imagine this kind of looks like. You have 2 data centers on each side. Each of them has basically a bunch of these switches that are cross-connected, and then a line system between that actually transmits the traffic long distance. So the switches are routers. I'm using the term interchangeably because software-wise they're actually you can't tell the difference because there's no routing running on the box itself. These things don't have long-haul optics. They just plug into a long-haul box, and then that does the actual transport. And then the controllers are regular servers, right? So we use our standard Google hardware. So it's a multi-core, high memory type kind of box. The deployment went over a number of phases. In the first light, so to speak, in the real world outside the testing lab was about 2 years ago, when we introduced this hardware sort of in parallel to our existing network in 3 of our data centers. So we had a little triangle, and started to play with the new network. And the network at this point, these new boxes looked to the existing network just like a regular box that talked ISIS and BGP. So the old network just saw some new adjacencies, but there's nothing unusual per se. And we moved some of the optical routes over to have bandwidth to play with, and we just kind of started playing with it. And at that point, the applications opted into the new network, so we picked some copy service or something like that, and directed its flow to the new network to test sort of how it behaves in real life. Then a little bit later, or actually sort of over the next year plus, we kind of rolled this out further across our network, still in parallel with the existing networks, but we tried to get to all the sites to have a more realistic network. And we switched to the real, to a fully OpenFlow controlled network. We tested how we can roll out new software releases on the controller boxes without interrupting the traffic on the network, failover, all these kind of things. And so then at the end of 2011, or late 2011, we actually had 100% of the traffic handled in one place, and then rapidly rolled that out to all places. So today, all of our inter-data center traffic is carried by this new network, so the old network is turned off. And also, in the meantime, then we rolled out our next release, our next sort of major internal release that does traffic engineering. So it solves the problem that I showed you on the slides, where if you have all your different flows and you want to guarantee that there's enough capacity, it places those flows in the network through the centralized traffic engineering and reacts to failures, et cetera, et cetera. So it's been running now for sort of roughly half a year seriously, and with traffic engineering since I believe January. So I'll tell you a little bit about our usage and our experience. So here's just a traffic graph, all the traffic on that network. And you can see kind of very rapid growth. Mostly that comes from moving traffic into the new network. Remember, like for most of the time in this graph, we actually were running two inter-data center backbones, and more and more traffic was moved over as we turned up new sites. And then in the end, actually, we also moved out some traffic from the internet-facing backbone to this that was suitable for this backbone. So we've been running a lot of traffic on it, and we've actually had pretty good experience most of the time. I think one of the biggest ones is that the iteration time for introducing a new feature or fixing a bug is much faster than it was in the previous network. And that's really for two reasons. One is that testing is much better in the new system, right? We have the simulation environment. We can simulate our entire backbone. So before you run it out in production, you can get a pretty high fidelity signal, whether it works or not, from your test environment. It's much easier to do that than before. And then also you have actually a simpler update process. Instead of having to update hundreds of devices out there in the real world, all of which are currently passing traffic and have a relatively thin CPU and little memory, and you have to go and update them, and etc. You have a few servers, control servers that you have to update. They're very, very powerful servers, tons of memory, etc., right? It's not a big deal. Plus, we do software rollouts in our data centers, with application servers all the time. So we have lots of tools that make this pretty easy. So testing was very important, and being able to roll out new features quickly. I'm telling our team, really, my goal eventually is push on green, meaning that whenever you have a build that actually passes all the submit tests, you push it out to production. And we're probably not really going to do that, but that's kind of the kind of fidelity that you would want from your testing environment. That really you could be confident that if your testing environment says this thing works, because your testing is so exhaustive, you actually trust that it will work, right? And your network engineering team can't find any additional bugs. So we're already seeing some benefits in utilization. The flow placement is better, not because it's theoretically better in the sense that you could get the same utilization by finely tweaking things in a traditional network, but the truth is you don't have time to finally tweak things all the time, right? Because 6 hours later, your network demands is different, and you need to go tweak it again. And tweaking has a risk in the old system, right? You actually can have unintended consequences because these protocols interact with each other in unforeseen ways. And so you don't really do it. And here, it's easy to tweak because it's all done in software, right? It's all done with a predictable, stable algorithm. And so you do it all the time, right? Makes planning much easier too. We're pretty happy with stability of the network. It's definitely meeting our SLA for our internal backbone. We have had outages, obviously, but actually far fewer than I expected. I was willing to have a lot more outages in order to get sort of make rapid progress on the actual goal of having a software managed backbone. So we're actually very happy with it. I can't give you percentage numbers here in the sense, we're saving X% of our network costs, because as you can see, right, this has just been running really for real. We haven't really fully changed our operating procedures to take advantage of all the of all the functionality, and also we haven't written all the software yet that we actually want to have sort of to enable higher level control and really application driven control of the network. So lots of things that we were hoping were opportunities with software-defined networking definitely happened. Here's a list, right? It's much easier to understand what's going on in your network. If you wonder what would happen if, right, it's easy to go to a test environment and just say, create that situation and kind of see what happens. Predictability is high, right? The explanatory power, so to speak, of looking at the network and saying, okay, here's the prioritization and why flows happen. You can convince yourself that it's correct, and so on. There's a number of challenges that we saw during development, and none of these challenges really are deal killers. So they're just things that you have to pay attention to. The OpenFlow protocol is still pretty early, but it's really complete enough to do something like what we're doing here, right? So it's certainly not done yet, but it's real and it's complete. So you can do real world network. You can run a real world network on it. Certainly no problem. I think one of the things that's going to cause some angst, and justifiably in the industry, is that if you have now a controller, you don't want your controller to be a single point of failure, so you have a backup controller. You need to have some kinds of master election, etc. That stuff is hard to get right, and so you just need to focus on it. Similarly, it's not totally clear how to, where you implement your software. We've taken a path to basically say, look, if something can be moved off the box, we want to move it off the box, and generally speaking, that's worked out pretty well. But not an exact science, and in our application, when the box comes up, it's a very prescribed way in how we configure things, so you don't have a super general bootstrap discovery kind of protocol, but in a more general environment, you might need to do a little bit more. Flow programming at some point, when we make a radical change in a network and you go update the flow tables of lots and lots of devices, we ran into some performance problems that we were able to solve. But so generally speaking, those were the kind of things that caused us some trouble. But as I said again, I think I expected, I didn't expect progress that would be that fast. So if you had asked me after, 18 months after we start for real, will we carry 100% of traffic on this new network? I would have said no, probably not. That's a pretty optimistic assumption. And also, it's really worked out, better than we had hoped. And I ascribe that a lot really to the easier way how you can write software when you write it in a standard environment, a reasonably powerful server, versus when you write it for your embedded processor that has little memory and little CPU and so on. So to conclude, I hope I convince you that OpenFlow in the WAN is a very interesting and worthwhile test case and actually application for OpenFlow, and that it's real enough to use. Right? We run literally our largest network. The internal network is actually larger than the external one in terms of the amount of traffic it carries. So we run our largest network 100% on OpenFlow. And even though it's early enough early in the process, it's stable and it's definitely meeting our requirements. I think there's a lot more upside potential there too, right? Our data center backbone is actually relatively simple because we don't have that many data centers, and so a lot of things where we see a strong benefit, I imagine you'd actually see a much stronger benefit if you had a more classical ISP network with a bazillion POPs and devices and so on to manage. And so we're looking forward to seeing if similar things can have a benefit too on more traditional backbones once that here supports OpenFlow. And I think if you take one thing away from this network, this clearly was sort of a bleeding edge effort, in the sense that 2010, when we rolled out the first test boxes on our backbone, OpenFlow wasn't even standardized. And in fact, I believe the ONF didn't exist quite yet. But even back then, it was actually good enough to do a lot of things just fine, right? Certainly in our environment that allowed for a little bit of risk on our backbone. So with that, I'm happy to take questions. And I'd like to also thank the teams really at Google who made this possible. This was not just, I talked mostly about the engineering part, writing the software, etc. But this actually was a hard problem in terms of really planning and executing the rollout on our backbone without having our users, the internal applications at Google, notice it. And also, I'm very, very grateful to work at a company where the network, the entire networking team, including network operations, is actually willing and eager to embrace change and seize the opportunities rather than just the risks of a network. And really, that was a big part of being able to go quickly and with measured risk, but still as quickly as possible, and actually roll something out in the real world. And so I hope that you all can benefit from that when you try to do this in your own network, so you know that at least someone has done it before and it actually works. So with that,
good morning.
Yeah. Okay, sure.
One of the questions that I had was, what are the challenges that you faced in terms of network planning? If you compare a legacy network to an OpenFlow network, the connectivity and everything changes, and what kind of challenges did you see there?
So I mentioned that a little bit on the slides. I think the testability and the planning actually and the predictability of the algorithms goes sort of hand in hand. The same framework that you can use for testing, you can actually use to test out various other scenarios where you have different flows and what happens under failure of links, etc. So it's a big instrument that you can use for planning. But the other part is that you know that because the centralized algorithm sees the whole network, it is going to place the flows if they are placeable, right? And so you don't have these situations which sometimes we had in the old network where theoretically the network fits the flows, but because of the way the protocols work, that solution is not actually found. And you have to go over provision a certain factor because you want to minimize the risk, or at least manage the risk that no solution is found automatically, and you have to go do a manual intervention after failure to make your, to make all your flows work. So generally speaking, I think our planning folks are happy, not deliriously happy, because we haven't built all the tools to actually do, to automate the planning, right? But I think I speak for them to say that this is already better than what we had, just because of the predictability and the ability to, when you have questions, actually go test it in a real world. Like if you have a question, like how will the system react if this demand comes in and then this link fails, you just set up a test in, all virtualized, and you will see what happens, right? And so you get comfort that your understanding of the system is actually correct.
Thank you.
Yes?
Stuart Raphael, IBM. First, I'd like to commend you on the tremendous pioneering work that you've done. It's quite an undertaking. The question that I have is, I know that you're not very clear, or it's too early to tell what the benefits are derived from the technology, but could you give us a sense of what some of the key criteria are that you will use in terms of determining what those benefits are? And then what is your gut reaction on the results of some of those benefits while not yet proven?
So I think in a high, and ultimately it is about total cost of ownership, right, of the network. How much do you pay to deliver X amount of capacity to your applications, and then also the service level to the applications, right? Do your applications understand what's happening in the network, and can they give you back requirement that you can translate for sure into the network? I think it's clear, even though we had to develop some hardware which has a sizable fixed cost, I think it's clear that we're ahead of, in the TCO equation already, meaning that we will save money amortizing the development of what we did, because it's already clear that the utilization improvements are going to be significant, right? In a large network, if you have a 10% utilization improvement at the same guarantees under failure, or better guarantees, that's worth a lot of money. And then also, I think we will find that once we have really our manageability, et cetera, all fully implemented, that we will be able to operate that network at the same or higher level of service with far fewer effort, like really integer factor less work, because you're going to have, the install, part that's basically the same, and you're going to have the repairs, O&M, etc. That's determined by the hardware and the lines. It's going to be the same. But then the configuration effort I expect to be much, much, much smaller. And also I think the monitoring and reacting to events is going to be smaller, because the system should really, in 99.x% of the cases, do the right thing automatically right away. So your notification will be, this link failed, everything's fine. Please open a ticket to get it replaced, right? And so we don't have really operational experience yet, the duration to kind of tell where we can take advantage of all of these, but I'm highly confident that this is a substantial cost reduction in terms of unit cost, your cost per megabit per month of bandwidth delivered at a certain SLA, right? So I think it's going to be a higher cost improvement than we could hope from any technology generation change, I think.
James Kemp, Ericsson, do you run MPLS on your backbone?
Not on this one, no. So the switch I showed you does not support MPLS. We did on the old one.
Rick Merritt from EE Times. Could you talk a little bit about that 10 gig switch you developed and how is it different from just a server? A little bit about what's inside the hardware and anything that you can say about the next generation of it.
I don't want to focus too much on the hardware because that is a side piece. We had to do it because it was not an option to buy something. We'd love to buy a gear, right? The right hardware kind of is available in the industry without the OpenFlow support, right? And so in the next version of our network, we might very well run someone else's gear. It just wasn't an option, right? And so this is there's nothing special in the sense that it's just a 10 gig switch, lots of ports, which you do need for scalability. We have a lot of traffic. But I would have loved to be able to buy this, and I'm confident actually I can this year or next. Yes? Or actually, we should switch mics.
Tao Gu with Center Networks. You mentioned scalability of this network. You mentioned this is the largest production OpenFlow network ever exists. I'd like to understand how many flows you're running on this network, and for the whole network, or how many flows per node?
So I think that depends on how you define flow, because two things. One, I want to advertise a talk later, I forget, is it today or is it tomorrow, right? By Amin Vadat of Google, that will talk in more detail about actually what we do in the software and the pieces behind it. So that will answer your question. But higher level, we actually aggregate flows in software outside the network and then tell the network to handle this category of flows in this particular way, right? Like you saw, we have in hardware, we have 7 QoS levels only, and for our application that's just fine because we actually do a lot of scheduling. Like there's a bunch of copy traffic on this network, and we do the scheduling of that copy traffic outside the network. So we don't make it the network manage it, but we have sort of a copy scheduler, and it tells the OpenFlow controller, I would like to have this much capacity between this place and that place at this priority, and then I shove in these copies, right, because they need to be done by 6 p.m., and then maybe some more real-time-ish copies that maybe should have no more than a 5-second delay, I'll put into this other flow that has a higher QoS on the network. And that's actually one of the advantages of this. You don't have to support all the functionality in the network. You now have sort of a more programmable machine, and so you can make it do a lot more things with the same hardware capability. So certainly the number of flows hasn't been an issue for us. But it is a simpler network than an ISP connecting 10,000 subnets with different customers.
So are those flows equivalent to routes, IP routes?
Sorry, I didn't understand the question.
Those flows equivalent to IP routes?
No.
Seiichi Kamura, NEC Big Globe. Thanks for giving this really exciting presentation. I really enjoyed listening to the talk. I had a simple question. I was worried about how your NOC took this new technology. Did they have to learn something new? If so, what kind of new technology did the NOC have to run? They have to run 24/365. So, this must have been a really big gap for them.
Yes, and so that's why I actually gave kudos really at the end, right? In the development cycle, we tried very much to bring in all the parties, including what we call NST, the monitoring, surveillance, and first line reaction, to make sure that they have the tools to operate this backbone. And with our simulation environment, we were actually able to develop these tools in parallel before we even had the hardware or a real working network. And that also makes it possible, and I don't actually know whether we did, to do training in a simulated environment. And so I think, yes, we did. Okay. So that actually went pretty well. And in many places, this is a simplification because they now can reason and observe the things that their users actually complain about, right? Their users don't call in and say, hey, MPLS tunnel XYZ, right, seems to be broken, right? They call in and say, I have this replication going on and it's seeing lots of packet loss, right? And now you can actually directly see what they're talking about, and you can say that, okay, right, we lost so much capacity in this region that, and you're priority 3, right, not priority 1. So, until we have this fixed in, you're going to see, 20% packet loss, and there's nothing I can do, right?
Thank you.
Yeah.
Could we make it just last?
Okay, last
two
question.
Yes. Okay.
Stan Kletko, Bakery. Actually, I would like to thank you for a very nice presentation. From the security perspective, you guys are moving to more centralized environment. Have you ever thought about the security of the controller? If somebody compromises the controller, what would be the security implications?
Yes, great question. So 2 things. First, I think intrinsically the security risk is lower because de facto, if someone compromises one router in your backbone, you're toast, right? They insert a default route, right? 0 cost to everywhere, and your network is done, right? So I think there's, single box compromise is lots of trouble. This actually in many ways is easier because there's fewer things that you have to kind of be careful about security-wise. Also, you can make sure that basically nobody in the network can really talk to that box, right? So the regular network links do not have reachability to the controller, right? Only the OpenFlow control port. And we do authentication with certificates, on the control link, so we feel pretty good about knowing that only this box can talk to the switch. Yes, this box could be compromised. I think the biggest risk, like all the time, basically is the insider risk, right? If someone in your NetOps team wants to do you harm and they have the password, there's an issue, right? But at the same time, I think in this thing, again, it's a software box, so it's easy to put in snapshotting, automated rollbacks off. Like, we have a snapshot of the config off the machine, so you can take another server and configure it as a replacement server, etc. So I think in a grand scheme of things, because you have all these software capabilities, you're going to end up in a better place than what you were before, where lots of people need access to your box because they need to log in, because they hand configure that box. Right? All of that is gone. Right? There's no login to the box anymore. Right? And so I think that intrinsically makes your network more secure. All right. Thank you very much.
Okay, thank you.